In this lesson, we'll discuss learning target number 1, describing the different states of matter, their properties, and factors affecting the state of a compound. We'll also describe in detail the behavior of gases using the kinetic molecular theory. The state of a compound is affected by how much energy the particles have, but also how much movement those particles are allowed in the overall structure. Solids have the chemical particles packed close together in what's known as a crystal lattice. A crystal lattice is just a three-dimensional repeated pattern. We'll represent it by 4 particles being close together in a square-like pattern. Now the particles in a solid are locked in the crystal through full intermolecular forces. These could be ionic forces, such as in an ionic compound, hydrogen bonds or dipole-dipoles, or even London dispersion forces if we're discussing a molecular solid. Because these particles are locked into position, they can't move very much, and they have a low amount of energy. But they are not still. In solids, the particles have what are known as vibrational motion. They jiggle around, but they're kept in their relative positions through their intermolecular forces. Because of this structure, we see the following properties of solids. They have constant shape because their building block particles are locked into position. They also have constant volume, and they're almost incompressible because the particles are packed really closely together. In the liquid state, particles have more kinetic energy. This allows them to temporarily break the intermolecular forces between them. And allows the particles the ability to slide over and past one another. This is also known as rotational motion because it causes the particles to spin. Liquid particles still have the same vibrational motion as seen in solids. Because the particles are not locked into position, liquids take the shape of their container, and they are also able to flow when poured. But they do have constant volume, and they're still almost incompressible, simply because the particles are still packed closely together. Compounds in the gas state have particles with even more kinetic energy. So much so that they're able to completely break the intermolecular forces holding the particles together. This allows the particles to spread out and move freely and independent of each other. The particles then are allowed to move laterally. This is known as translational motion. The particles do still have rotational and vibrational motion as seen in liquids and solids. Because the particles can move their relative positions, gases also have variable shapes. They also have variable volumes. The gas particles will expand out from each other until they hit something solid. Therefore, the volume of the gas is the size of the container you store it in. Because gas particles are so spread out, they can actually be squished closer together, making gases compressible. Discussed below are the two main factors affecting the state of matter. The first being the strength of the intermolecular forces that can be formed between the compound's particles. The stronger the intermolecular force a compound can make, the more locked into position the particles are in relation to each other. This makes the substance more likely to be a solid at room temperature. Remember, we discussed this in Unit 1. If we draw a chart going from the weakest intermolecular forces to the strongest intermolecular forces, substances with strong forces like ionic compounds such as NaCl are solid at room temperature. Compounds that have medium strength forces like dipole-dipole or hydrogen bonding will be liquids at room temperature. An example would be water, H2O. And then substances that have very weak forces can't keep their particles held together at all, making them gases at room temperature, such as nonpolar carbon dioxide. However, if you change the temperature of the compound, you can make it any state, depending on how much energy you provide to the particles. By increasing the temperature, you provide the particles with more kinetic energy, or more motion. If enough energy is gained, the intermolecular forces get broken and the substance changes state. For example, taking ice and changing it into steam. If you start by heating ice, you're providing energy to the water molecules to change full hydrogen bonds into temporary hydrogen bonds. This causes the ice to melt into water. When you heat the water, the molecules move faster and start developing translational motion. This allows the water molecules to completely break the hydrogen bonds holding them together, and the water boils, creating steam. This can be done with any type of compound. Another example would be to take carbon dioxide gas and cool it. As the particles slow down, the weak London dispersion forces start to be able to hold the particles together temporarily, and the CO2 gas will condense into liquid CO2. If cooled further, the particles slow down enough so that the London dispersion forces can lock the particles into position, creating CO2 solid. We know this as dry ice. The kinetic molecular theory describes the movement and behavior of gases in more detail. It's a scientific model that explains the general behavior of an ideal gas, a hypothetical perfect gas. Gases in real life don't exactly follow these following statements, and they vary slightly depending on which gas you're discussing. So why do we have the kinetic molecular theory? When we do calculations involving gases, they can be quite complicated if we want to take into account all of the idiosyncrasies of the particular gas we're using. We would have to include many terms in our math equations to correct for the slight variations in the behavior for the gas. Now in this course, we don't need that level of accuracy. If we assume that the gases all behave and follow the rules like an ideal gas, it makes our gas calculations much simpler with less terms. If you go on into university chemistry, you may then start to use real gas law equations that correct for the slight variations of the gases. The kinetic molecular theory of gases describes an ideal gas as having no volume. This is because the gas particles are so spread out in a sample that if you squish them together so that they were next to each other, you would actually have a very, very small amount. Since the gas expands to fill its container, when we do calculations, we just use the volume of the container for the volume of the gas. Secondly, the theory states that there are absolutely no intermolecular forces between gas particles. However, in real life, some highly polar and fully charged gases are still influenced a little bit by their charges. Number 3, gas molecules move randomly in all directions in straight lines. In real life, gas particles are slightly affected due to gravity, but we're going to ignore that interaction in this course. It's not going to affect our accuracy very much. It is a very slight effect because the gas particles have such a small mass. Statement 4, collisions between molecules and the container are perfectly elastic. That means that there's no loss of kinetic energy whenever a gas molecule hits another gas molecule or hits the container. And finally, the 5th statement says that the average kinetic energy of a gas is directly related to the gas's temperature, which means if you double the temperature of a gas, then the particles move twice as fast. Now, depending on the gas you're using, this isn't exactly true. It might be you double the temperature, the speed increases by 1.8. It might not be a perfect relationship, but it's pretty close, so we'll make this assumption to make our calculations easier. You need to know the 5 assumptions of the kinetic molecular theory of gases, so that when you're asked, you can describe how an ideal gas behaves.